All right, in our previous video, we were looking at difference between permutations and combinations. And we looked at this example of picking 5 animals. We can generalize this idea of picking things. Suppose I have n objects, and I want to pick k of them. And there's going to be some assumptions that are going to be important here. The first is that the objects are distinct, which means I can tell the difference between the first and second, fourth or fifth, and which one is which matters. So they're distinct. Also, the order that they appear matters. So if I pick the first one first and the 8th one second, that's different than picking the 8th one first and the first one second. Okay. If this is the case, the question now is, how many ways is there to do this? And I could think about this in terms of the tree diagram, but this is going to get messy really fast. Right, so my first pick, there's n things that can happen. For each one of these, there's going to be n minus 1. For each one of those, there's going to be n minus 2, and I can keep going. But I'm going to try to use the principle of counting to deal with this. So the idea is I've got n objects. I'm going to pick k, and again, the order matters, and the objects are distinct, so I can tell the difference between the objects. Okay. If this is the case, I can think of it this way. So if I'm going to have k choices. And if I think of each of these cases, each of these k picks as being, think of these as like a cup or something I'm going to put something in, I'm going to take these n things, and the first thing I'm going to do is take one from here and put it there. How many ways are there for me to do that? Well, since there's n objects, there's n ways I could put it in the first bin. And I got to be careful here. I'm going to assume this is without replacement. That's important. Now there was originally n. Okay. But now, having chosen 1, there's going to be n minus 1 objects in there. So that means when I go to pick a second object, the number of ways that could happen is that there's going to be n minus 1 left. And once I take that out and put that one in the bin, now there's going to be n minus 2 left. So for my third choice, there's n minus 2 ways I could do that. And likewise, now for my fourth choice, there's n minus 3 objects. So there's going to be n minus 3 ways I could do that. And I'm going to keep going until I get to the kth pick. And after the kth pick, there's going to be n minus k plus 1 object still left. So there's n minus 1 plus k options for that kth pick. Okay? And now for the total number, I can just multiply those things. So I'm going to get n times n minus 1 times n minus 2 times n minus 3, and I keep doing that until I get down to n minus k plus 1. Okay. If these things are the case, if we don't have replacement, the objects are distinct and the order matters, we're going to call that permutations. Okay. So the number of permutations, so I'm not talking about all the permutations, I'm talking about how many there are. I'm going to choose k of these things. And that's coming from a collection of n distinct items. And I'm going to use without replacement. And it's important to note that the order matters. that's going to be called the number of permutations, and the notation, and I'm sorry, I don't like this any more than you're going to like it, is P for permutations. I'm choosing from N, and I'm choosing K from there. So we use small subscript N on the left, capital P, small k subscript. And that's going to be N times N minus 1 times N minus 2 all the way down to N minus K plus 1. Okay, this notation is going to be very important, and we're going to use it regularly. Now, yes, this is terrible notation. I don't like it, but here it is. And also, there's going to be a lot of situations where we're going to get down and talk. There's going to be a 0 in one of these items. So by definition, I'm going to call 0 factorial 1. Oops, I'm going to be careful here. And we're going to make use of this idea of I'm going to take n times n minus 1 times n minus 2. We're going to use something called the factorial notation. Let me start over here. So to make this notation a little more tractable, I'm going to define n factorial to be n times n minus 1 times n minus 2 times n minus 3, and you keep going all the way down until you get to 1. And again, by convention, we're going to say 0 factorial is equal to 1. And the reason we do this is it just makes everything easier, and it just kind of makes sense. You can think of this as there's only one way to pick 0 objects. Okay, so that means if I'm talking about number of permutations for choosing k items, we just said this is equal to n times n minus 1 times n minus 2 all the way down. Then I stop at n minus k plus 1. That's not what's going on here. So I'm going to amend this. And I would like to be able to make use of this factorial notation, because it's going to turn out to be very convenient later. If I were doing this in terms of factorials, I could just keep going. But this is not equal to this. If I multiply this, I also have to divide by this same thing. And by doing that, these two expressions are the same. And what's nice about this is the numerator is now n times n minus 1 times n minus 2, and I keep going down to 3 times 2 times 1. The numerator is n factorial. And notice the denominator is n minus k, and I multiply that by, subtract 1 and multiply, and I keep going down. So that is n minus k factorial. Right? So we have this notation to talk about the number of permutations where I'm picking k objects from a set of n distinct objects. I can write in this notation. Okay, so from our previous example, I had 5 animals. I'm going to pick 3 and assume order matters. Then in that case, this is permutations for picking 3 animals from a group of 5. So we call this, use this notation to refer to that. This is going to be what? 5 times 4 times 3 times 2 times 1 divided by 3. Oops, sorry, this should be 5 minus 3 factorial. So that's going to be 2 times 1, 2 factorial. It's 5 times 4 times 3, and this gives us the exact same thing we got before. Okay, now it's really important to be careful and read questions very carefully. So for example, suppose we have license plates. And a license plate is made up of a combination of letters or numbers. let's just assume, just for fun, that we have 6 digits. The question is how many? So first of all, this is not a well posed problem. There's many ways to interpret this. What if we're allowed to have repeats? So for example, you could have A. So that means each time you do this, you could reuse a number. So in this case, each of these things could be either a letter or a number. So there's 36 options. And each license plate has 6 slots. First slot then could have 36 potential numbers in it. Because we're allowing repeats, once I put a number or letter in here, there's still going to be 36 left that I could put in here. And so the total number is 36 raised to the 6th power. And this turns out to be 2,176,782,386. And that is what we in the business call a big number. Suppose I say repeats not allowed. So in this situation, once I put a number in the first thing or a letter, I can't go back and reuse it. So just like before, I've got 6 slots. Initially, I have 36 options. If I'm not allowed to repeat anything, once I've used that, it's gone, and now there's only 35 options. So only 35 could go there. For the third, now I've removed 1 object, so now there's only 34 left. And I can keep following that pattern. So the number is going to be 36 times 35 times 34 times 33 times 32 times 31. And that comes out to be 1,402,410,240. Okay. Also note that's equivalent to saying 36 factorial divided by 36 minus 6 factorial, or 36 factorial divided by 30 factorial.